Hello, welcome to another domains video from the Institute of Physics. This one is going to be about the separate gas laws, and next time we're going to look at the ideal gas law and what it means to be at absolute zero. So remember, before we start, that we're talking about particles. We're talking about this kinetic theory of gases. So our kind of core assumptions are that all of the particles are points. They've got no dimension, unlike this rather helpful Wikipedia picture, and all of the collisions between them are perfectly elastic. The kinetic theory of gases, this was proposed by Bernoulli in 1738. He was the first person to sort of talk about air pressure in terms of particles, in terms of molecules. He visualized them shooting around. In fact, this lovely picture is from his book, where he published his ideas. The fact that nobody believed him is a fairly unfortunate but fairly common part of history if you look at scientific discovery over the ages. What he said was that if you increase the pressure on a vessel, then the volume of it will decrease until you've got enough collisions between those molecules and the surface in order to provide a sufficiently large force. So he was talking about the idea of gases in terms of molecules or particles having collisions with the wall, and that change in momentum giving you a force per unit area. So really relatively advanced for his time. He also made the link between temperature and pressure and volume a little bit. So he said if you heat up a gas, those molecules will move faster, and so the collisions will be more energetic, and so there will be a higher rate of momentum change and therefore a higher force. He didn't phrase it quite like that, and that may be partly why it was kind of forgotten or ignored or bypassed. And it may be that just we weren't quite ready for it, because in the time that Bernoulli was doing this was a little bit before the urgent kind of industrial need to understand gases, which drove so much of the rest of the gas laws. So the first one is Boyle's law that we're going to look at. And on the left, you can see a defense of the doctrine touching the spring and weight of the air, which was proposed by Mr. R. Boyle. This is absolutely a great little book, published as you see it. This is a photograph of his original book. Boyle was involved in the Royal Society, and if you look at the history around this time, there's Hooke involved in a lot of these things. I think Hooke was an apprentice of Boyle's, and so you've got a lot of this kind of really famous, brilliant kind of science going on. The classic demonstration here is linking the pressure, as you can see in this middle one. You've got a pressure gauge and the volume. Now this middle video here is the classic experiment. I have increased the pressure on this fluid, and so I've basically pumped this up, so I've compressed that gas, that very small volume of gas at the top there, and I'm measuring the pressure required to do that. And so as I allow the pressure to decrease, if you like, the volume will increase. And so there's a direct link, and you can graph this. This is a very fancy, relatively fancy piece of kit. Most physics departments have these to allow you to demonstrate Boyle's law. You don't need a fancy piece of equipment, and in fact, with a pressure gauge that's very cheap and a syringe, as you can see on the right here, you can show that there is a link between the pressure and the volume that a gas takes up. We're talking about things at constant temperature here, and so as you can see, as I squeeze this syringe, unsurprisingly, I'm compressing the gas, and the pressure of that gas increases, as you can see on my in there. Thanks to the beauty of open source, we can, or the fact that after a certain time, publications become kind of, if you like, free to use, we can look at Boyle's original data. And so on the left hand side here, this is Boyle's original data, and on the right I've plotted that original data, the pressure against volume for a gas, and we can see that we've got some kind of relationship here where the pressure is proportional to 1 over the volume. And in fact, what he ends up saying is pressure times volume, it gives you some kind of constant. You don't. If you want to do this more qualitatively, then there are lots of ways of doing this. This is a balloon hooked up to a vacuum pump. I've got a little vacuum chamber here. In the left-hand one, I've left the top open to the atmosphere, and you can see that as I reduce the pressure inside the vessel, atmospheric pressure causes the balloon to expand until such point it pops. And in the right-hand one, there's actually a cork in the top. And so what we're doing here is we're just allowing the very small quantity of gas that was inside that balloon to expand. It doesn't expand as much because, don't forget, it is constrained by that elastic balloon. So these are quite nice qualitative pressure volume kind of relationship demonstrations. You don't have to even have a vacuum pump. You can do a lovely version of this with a vacuum or similar, the kind of wine saving vacuum pump, and a bottle. Pop a marshmallow in it, pump the air out, marshmallow will expand. Do the same with the syringe. Really lovely demos. So the next to look at is Charles's law. Charles says when the pressure on a sample of dry gas is held constant, the temperature and the volume will be in direct proportion. And so in essence, if I heat this gas, then it will expand. This is the basic principle behind which the hot air balloons, such as the one that I photographed here, this was going over my house rather conveniently about a week ago. This operates on the fact that a higher temperature gas has expanded, it's less dense, and therefore your hot air balloon will float. In equation terms, that looks a little bit like this. So V is proportional to T, so V over T is a constant. And so that's two things, two parts of this pressure, volume, temperature relationship that we have found equal some kind of a constant. And so already you can see that we might be heading towards unifying these things together. So what haven't we looked at? Well, we haven't looked at pressure. So I've had a hunt around and I've found Amundsen's law. Sometimes we use the Joly bulb, or sometimes we call this the pressure volume law, or there's various names for it. As always, I really encourage you to dig into the background of this because there's so much good science going on in this period, and there's all sorts of controversy and scientific fraud going on. It's really lovely to fill your lessons with this extra context. And so having a hunt around, I found a couple of images that I can use because we're slightly restricted in this with you. And here they are. Here are two Coke cans that have been left in the sunlight. And so as the temperature has increased, the pressure inside that vessel has increased, and you can see it's caused them to deform. And on the right hand one, you can see that there is a mobile phone battery. Again, this is a stock image. And this has got hot, and it is expanded and has actually caused the phone to kind of break. So I really urge caution. Please don't try and reproduce either of these because they're quite dangerous when you've got high pressures and high pressures being contained. Then if something goes wrong, there's a really big release of energy there, and that's really unsafe. However, you can use things such as the Joly apparatus or Joly's bulb sometimes, and here's a really simple version. What I should have done with this experiment is I should have placed the bulb in a very low temperature environment, so in the freezer, and then I should place it in this hot water. Unfortunately, I don't have access to a freezer at work where I filmed this, and so what I've done is I've got my room temperature bulb. I've popped it in some boiling water, and you can see the needle just about flickers. We get a little bit of an increase in temperature. Again, because of the current restrictions, we're not using Bunsen burners in the lab, or I would kind of take this from iced water up to boiling over a Bunsen burner. Okay, slightly difficult thing to do. So with problems like this, with these kinds of investigations and experiments, particularly in the current time, I really recommend sites such as PhET, PhET, really good simulations. They have got excellent simulations that you can use for all of the gas laws. So for example, here you can see a couple of scenarios. You can see that we have got a 300 Kelvin kind of box with a number of particles, and in the next image that's gone up to 709 Kelvin. These are arbitrary. I'll take a snapshot of the simulation that's running, and the pressure has increased enormously. The volume is fixed. Because it's a simulation, you can do a lot of fun stuff with this. You can actually use this sim. You can heat and cool things. You can compress. You can kind of slide it around and compress the gas. You can let some gas escape. You can add some different particles of different weights, and you can have a bit of a play. And I really encourage you, and at some point, to use a couple of simulations like this in order to allow the students and allow yourself to talk about what's going on internally. Again, you have to be a little bit careful because they're only a model of what's going on. They're a simulation of what's going on. Actually, the real thing is quite complicated. And remember that as soon as your points in your your point molecules are no longer points, actually some of these relationships start to break down a little. So there are loads and loads of other good resources out there for you to have a look at and for you to use. I've picked one at random here. There's some of the NASA things. A few years ago they did a lovely project down in Nemo, which is the undersea lab. The undersea lab's at 3 atmospheres pressure because it's 30 meters below the surface of the sea. And Tim Peake here, who we know as an astronaut, he did a number of things such as opening crisp packets on the surface and opening them down underneath. He flew a little helicopter around and lifted some masses on dockside and did it again, and was able, because the atmosphere was roughly 3 times thicker, if you like, there were 3 times as many particles, 3 times as many collisions. That little helicopter was able to lift roughly 3 times as much weight. And so that's a really nice kind of application, a slightly surprising kind of context in which to talk about all these things. So next time we'll tie all of these things together and we'll look at the ideal gas law and we'll look at absolute zero. Thanks for joining me. See you next time.